Welcome everyone. In this lecture, we will continue with the basic definitions of general theory of Lie algebras. So, we will begin with homomorphisms. So, let G and G dash be two given Lie algebras. A homomorphism from G to G dash, it is first of all a C-linear map. Let us call it pi. So, it is a C-linear map satisfying the following condition. So, if you take pi of the bracket xy, so that is supposed to be equal to the bracket of pi of x, pi of y, and this should be true for all x, y in G. So, that means this pi is not only a C-linear map, it also preserves the Lie structure. So, we use both homomorphism or Lie homomorphism to denote this kind of maps. So, this pi is called Lie homomorphism. Okay. So, now we will define other terminologies like subalgebra, ideals and so on. So, what is a subalgebra? So, let us say G be a Lie algebra. A subspace G dash a subspace G dash of G is said to be a Lie subalgebra if whenever we take the product bracket xy, that should be in G dash for all xy in G dash. So, that means you have this Lie bracket defined from G cross G to G. When you restrict that map to G dash cross G dash, then it should be a map from G dash cross G dash to G dash. So, when you take this bracket map restricted to G dash cross G dash, then it should define a map from G dash cross G dash to G dash. So, that is what we call it as subalgebra. So, now one can easily check, this is easy exercise. So, G dash with respect to this restricted map is indeed a Lie subalgebra. So, this itself is a Lie algebra and which is also called Lie subalgebra of G. So, we will be interested in various Lie subalgebras of given Lie algebra. Okay. So, before that we need to define the most important object called ideals. The ideals, it is a subalgebra, yes, subalgebra or even a subspace just to begin with. Okay. A subspace I of G is said to be an ideal if whenever we take the bracket xy, that should be in I for all x in I and y in G. Okay. So, this is like very similar to what we define ideals for the general associative algebras. Okay. But since the bracket that we have here, it is skew symmetric. So, that means the bracket of xy is same as the bracket of minus yx for all xy in G. So, because of this we do not have any difference between left ideal, right ideal or two sided ideals. All of them are same here. Okay. The left ideal, right ideal and two sided ideals, all these concepts will be same in the theory of Lie algebras. So, now we have this ideals and subalgebras. So, now given this homomorphism, so one can actually define immediately what is called isomorphism of Lie algebras. So, we say G and G dash are isomorphic as Lie algebras if there exists a bijective homomorphism between them. If there exists a bijective homomorphism from G onto G dash. So, it is an easy exercise to see that if you have a bijective map homomorphism from G to G dash, then the set theoretic map that is defined, the inverse of that map pi, which we denoted by pi inverse. So, that will be again Lie algebra homomorphism. So, that is easy to verify. I will leave it to you too. So, that is why we demand only bijective homomorphism from G onto G dash, because the inverse becomes automatically Lie homomorphism. So, once we have these terminologies, now it is easy to actually state the first theorem, first isomorphism theorem of first isomorphism theorem. So, let us actually state it. Here is the theorem. So, this theorem is very similar to what you have seen in other algebraic, for other algebraic objects. So, let us say G and G dash both are given, both be given Lie algebras. And let us say we have a map Lie algebra homomorphism from G to G dash. So, this is a Lie algebra homomorphism. So, then once we have this Lie algebra homomorphism, we will be able to define the following objects. The very first object is what is called the kernel. The kernel is defined as it is for the C linear maps. This is those x in G such that when you act pi on that x, that should be 0. So, this is what called a kernel of G, and it is easy to verify that this kernel is indeed ideal inside G. So, this is an ideal of G. So, we denote ideals by this tilted triangle. So, similarly, we also have this image of pi or pi of G. So, this is set of all the image pi of x, x in G. So, this is a subalgebra of G dash. So, this is a subalgebra of G dash. So, now given these two objects, we can easily see that we can define this quotient space G modulo the kernel of pi. So, this is by definition you take all the cosets x plus kernel pi such that x in G. Okay. One can make, so this is a quotient space. So, this can be made into a Lie algebra. By defining the following Lie bracket. So, we define the Lie bracket x plus kernel pi bracket y plus kernel pi. So, this is the Lie bracket that is induced from the ambient Lie algebra G. So, this is defined to be the bracket x y plus the kernel pi. So, I will leave it to you to check this indeed defines actually Lie algebra structure on G modulo kernel pi. So, this is defined for all x, y and G. Okay. So, this Lie bracket makes this G modulo kernel pi as a quotient Lie algebra. So, now with this we have actually the following first isomorphism theorem. So, with these notations we have this induced map pi tilde which is defined from G modulo kernel pi onto this pi of G, which is the image of G, image of pi. So, the map pi tilde is defined to be pi tilde of x plus kernel pi is mapped to pi of x. So, now one can easily check this is indeed a bijective map from G modulo kernel pi to this pi of G. So, as a C-linear map it makes sense, and as a vector spaces they are isomorphic. So, then you can easily see that. So, these two are actually, this pi tilde that is defined here is indeed bijective map, and because pi is to begin with Lie algebra homomorphism. So, from this one can easily check this pi tilde is also a Lie algebra homomorphism. So, that means this pi tilde indeed defines an isomorphism. So, this is an isomorphism. So, isomorphism of Lie algebras. Okay. So, I will leave it to check these facts. So, this is somewhat easy to actually check. So, now if we take for example as an examples. So, if we take any one dimensional Lie algebra, so that must be abelian, that is we have already seen. But if we take any two one dimensional algebra, that must be isomorphic to any two one dimensional Lie algebras must be isomorphic. Similarly, if we take two dimensional Lie algebra, then one can prove that either it will be isomorphic to abelian Lie algebra or it will be isomorphic to the following one. Okay. So, any non-abelian two dimensional Lie algebra is isomorphic to the following Lie algebra, which we denoted by G2. So, this is the C span of E11, E12 which sits inside GL2. So, recall that Eij is the standard basis of GLN, and we take just 2 by 2 matrices E11, E12 and then span this. So, then this subspace inside GL2 is a subalgebra. So, this is a two dimensional non-abelian subalgebra, and any two dimensional non-abelian subalgebra, any two dimensional non-abelian Lie algebra will be isomorphic to this algebra. So, the Lie bracket is easy to compute. If you compute E11, E12, the bracket, so this is going to be E11, E12 minus E12, E11, which is going to be just E12. So, again the bracket E11 with E11 will be 0 and E12 with E12 will be 0. So, now using this Lie brackets, it is easy to check G2 is indeed Lie subalgebra of GL2. Okay. So, now we will define the most important objects in the structure theory of Lie algebra, which are called simple Lie algebras. So, what is simple Lie algebra? So, a Lie algebra G is said to be simple. Okay. So, we will be only concerned with finite dimensional Lie algebras in this course. So, you can assume that just we are dealing with only finite dimensional Lie algebras. So, let us say G is given Lie algebra. So, this is said to be simple if it should satisfy two conditions. First condition is that the dimension of G must be greater than 1, so that we avoid the trivial cases. And the second condition, the only ideals that are there in G of G are nothing but the 0 and the full ideal G. So, it is easy to see that the trivial ideals 0 and G, they are ideals inside G, and these are all the only ideals of G inside G. So, in that case we say that G is actually simple Lie algebra. So, this is just a simple definition. So, now we can also define what is called the center of G. The center of G is defined to be those elements of G which commutes with all other elements of G. So, that means you collect those x in G such that the bracket x y is 0 for all y in G. And I will leave it to you to check, it is easy to check that the center must be ideal inside G. So, this is an ideal. Now, we also have what is called the derived subalgebra or derived algebra of G. The derived algebra is defined to be the span of all brackets. You take span of all bracket x y where x and y comes from G. Okay. And this is indeed again subspace and it is an ideal inside G. So, the bracket G G is an ideal inside G. And it is an easy exercise that if you have a subspace, let us call it I is a subspace of G. Suppose I actually contains the derived algebra. So, then I must be ideal inside G. So, that is easy to see. Again similarly, if I is contained in the center, then again I is an ideal in G. So, this is something very easy to verify. So, I will leave it to you to check. So, now given two subspaces motivated from the derived algebra, one can actually define the bracket of H1 H2. So, generally given two subspaces H1 and H2 of G, we define the bracket H1 comma H2 to be the span of all this x y such that x is coming from H1 and y is coming from H2. Okay. So, in case if you start with H1 H2 to be ideals, okay, to begin with their ideals. So, then it is easy to see that this bracket is also an ideal and it is indeed contained in the intersection and all of them are ideals. Okay. This H1 H2 the bracket is ideal inside G and H1 intersection H2 this is an ideal in G and H1 plus H2 that also will be ideal inside G. H1 plus H2 it is just the sum of all elements from H1 and H2. So, these are all some simple exercise that actually part of the general theory of Lie algebras. So, to understand this adjoint representation one needs to understand all the ideals of G. So, that is why we need to know some information about the ideals, that is why I am recalling all these results. So, here is the important theorem that actually gives you the correspondence between the ideals of G and then the ideals of its image under some Lie homomorphism. So, this theorem again I am not going to prove it, I am going to only state it. So, this is called lattice isomorphism theorem. Okay. So, if you start with a surjective Lie algebra homomorphism, let us call it pi. Okay. Let us say pi is a surjective Lie algebra homomorphism. So, then using this map pi, one can actually define this following bijection between the ideals of G containing the kernel and the ideal of the image. So, what are all the sets? So, here is the set on the right side. You take the set of all ideals of G containing this kernel pi and then you can define this one-to-one correspondence between this set to the following set, the set of all ideals of this pi of G, which is G dash. So, what is the map? There is this natural map. You start with an ideal here I inside G, which let us say contains the kernel. So, then you just map that to pi of I. And similarly, if you start with an ideal I dash inside G dash, then you map that to just pi inverse of I dash, then clearly pi inverse of I dash contains this kernel pi, which is pi inverse of 0. Okay, and it is easy to verify that this correspondence is indeed bijective correspondence. So, this is indeed bijective correspondence between these two sets. So, this gives actually informations about the ideals of G containing kernel and what is happening in the image. Okay. So, now we will actually see some more important examples. So, like I said, this course will be about the representations of GLN. So, we need to understand what are all the various subalgebras, those are important subalgebra of GLN. So, they actually help us to understand the structure of GLN. So, let us actually slowly recall. So, like I said, our running example will be always GL2 or SL2. So, let us fix some notations. So, what is GL2? So, GL2 is the set of all 2 by 2 matrices, and it is clear that it is spanned by, so the dimension of GL2 will be 4. So, this is spanned by E11 and then E12, E21 and then E22, and this SL2s, so that will be traceless matrices from this GL2. So, this is those x in GL2 such that the trace of x must be 0. So, then it is easy to see that this is again spanned by 3 elements. So, because the dimension of SL2 is 1 less than the dimension of GL2, which is 3. So, we denote the standard basis of this SL2 by x, h and y, where this x is just the upper triangular matrix 0, 1, 0, 0. So, that means this is 0 E12, and this h by this diagonal matrix 1, 0, 0 minus 1. So, this is nothing but E11 minus E22, and similarly this y by this lower triangular matrix 0, 1, 0, 0. So, this is E21. Then it is easy to check if you compute the commutator between them, then the bracket xy. So, this is going to be xy minus yx, which is E12 times E21 minus E21 times E12. So, which is going to be E11 minus E22. So, this is nothing but h. Similarly, if you compute the bracket between hx, then you get 2x, and then hy is going to give you minus 2y. I will leave it to you to check. So, this is the most important actually bracket table for SL2. So, with this basis, bracket of these elements given as follows: the bracket of xx, hh and yy, so that must be 0, and then the bracket of hx is going to be 2x, and the bracket of hy is going to be minus 2y, and similarly the bracket of xy is going to be h. So, this is the most important structure constants of this SL2. Okay, now let us see how one can use this to understand the structure of SL2. Okay, then later we will actually try to understand the structure of GL2 and more generally SLN and GLN. So, it is easy to see that GL2 is nothing but direct sum of SL2 and this identity matrix 2 by 2 identity matrix. Now, this identity matrix going to actually commute with all the elements of GL2, and now one can easily see that this is going to be actually direct sum of two Lie algebras. So, we will define the direct sum later in this course. So, now what I want to prove? I want to prove that this SL2 is indeed a simple Lie algebra. Okay. So, this is first example of simple Lie algebra. So, here is the result. SL2 is a simple Lie algebra. So, the idea of proving this SL2 is very important. Again, here implicitly we are using the representation theory of SL2. Okay. So, basically we are making SL2 act on itself. So, let us see how one can prove this. So, note that SL2 is nothing but the C span of these elements x, h and y with the Lie bracket. Xy is h and then hx is 2x and then hy is minus 2y. Now, from these formulas we can easily see that the bracket hx, hy being like 2x and minus 2y and hh is 0. So, if you look at this add h map from SL to SL2, so then you can easily see that this add h map is diagonalizable. So, what are all the eigenvalues? The eigenvalues being 0, 2 and minus 2. So, the add h, okay. So, let us use this the order in these spaces like this. So, h, x, h and y. If you use that order basis, then the matrix of this looks like, so hx is 2x and then hh is 0 and then minus 2. So, this is the matrix corresponding to this add h. So, now because of this, if we have any ideal inside SL2, so let I being non-zero ideal inside SL2, so then we can restrict the action of add h to this I. Then this has to map I to I. So, that is the first observation. Since add h is diagonalizable operator on SL2, if we restrict that operator to I, that also must be diagonalizable. So, this is a diagonalizable operator. So, now because this is diagonalizable, so and all the eigenspaces of add h is one dimensional for SL2 and there are 3 distinct eigenvalues 2, 0 and minus 2, then you can see that this add h restricted to I also must have some eigenvalue non-zero, some eigenvalue and with a non-zero eigenspace. Since all the eigenspaces of SL2 is one dimensional, so that tells us that the eigenspace, at least one of the eigenspace, okay, at least one of the eigenspaces. So, let us call it like V2, V2, V0 and V minus 2. So, basically V2 is spanned by x, V0 spanned by h and V minus 2 is spanned by y. So, then it is clear that at least one of the eigenspaces lie inside h, inside I. So, without loss of generality, one can assume that just let us say x is there, okay, just Cx is there inside I. Then this would imply that the bracket xy which is h is inside I and that would imply that the bracket hy which is minus 2I which is in I. So, this implies that entire SL2 is subspace of I. So, that means we have I equal to SL2. And the proof actually is very similar if you assume that Cy is subspace of I or H is subspace of I. If H is subspace of I, then you can easily see that Hx, the bracket Hx which is 2x, that is also inside I, that will imply x is in I. Similarly, if Cy is subspace of I, then the bracket yx which will be minus h, that will be in I, that also will imply I equal to SL2. So, this proves that SL2 is simple Lie algebra. So, now using this and using this decomposition GL2 equal to SL2 direct sums C times identity. So, we will actually determine the structure of GL2 as well. Okay. So, we will actually continue to study the structure of GLN in the next class. I will stop here. Thanks.